In the last lesson, we looked at how we can index and slice a multi-dimensional array. In this lesson, we're going to further manipulate array shapes. A lot of the functions and methods we're going to use in this lesson, you'll see quite often in this course, so it's important that you get familiar with them now. The first function we'll look at is ravel, which flattens a multi-dimensional array and returns a one-dimensional array. Suppose I had an array with 9 elements from 0 to 8 that was reshaped into having 3 rows and 3 columns. We can flatten this array back into a single-dimensional array by calling raveled array is equal to the array itself x.ravel. Go ahead and print raveled array, and it flattens it into a one-dimensional array such that it now only has a single row. The flatten function does the same thing as ravel. We could try this out by setting flattened array is equal to the array itself dot flatten. Print flattened array. And indeed, it still outputs a one-dimensional array. The difference between the two cannot be distinguished with simply this print statement. But it's important to know that flatten always returns a copy and allocates new memory, whereas ravel would return a view of the original array. Why is this important? Well, if I were to modify an element in the array returned by ravel, it would modify the original array x as well. We could try this out by setting the element of the raveled array at index 2, we can set it to be 1,000,000. Print the raveled array, and indeed it is 1,000,000. But if we also print the original array x, clearly the change is reflected in both arrays. Whereas with flatten, since it returns a copy of the array, modifying the copy will not have an effect on the original array. For clarity, we'll revert our original array to have its initial value by rerunning all the cells and removing the code that we put. We will modify the flattened array to also have a value of 1,000,000 at index 2, 1,000,000. Do not put any spacing in between. There you go. If we print the original array, notice that it has no effect. Even though using ravel is much faster since no new memory is allocated, the side effect being that it's not as safe in the sense that one must stay mindful that any changes to the raveled array are also reflected in the original one. That is all for flattening and raveling. On another cell, we'll declare an array, a new array with 9 elements. Y is equal to np.arrange9. And now what we can actually do is, instead of using reshape to make this into a 3x3 array, as we did previously, we can set the array shape directly with y.shape is equal to a shape of 3 rows and 3 columns, and printing y results in an array of 3 rows and 3 columns as predicted. We can also flip a matrix over its diagonal, that is, obtain its transpose, by switching the row and column indices. You can do so by printing y.transpose, specifying an argument of none, and indeed it does flip the matrix over its diagonal as the rows and columns have been switched. An equivalent approach to this would be to use the t attribute, y.t, which has the same effect as the transpose function with no arguments given to it. We can also resize an array. Resizing not only reshapes an array, but it also modifies it such that if the new array that we're resizing it into is larger than the original array, then the new array is filled with repeated copies of the array that's being resized. Our original array is a 3x3. We can resize it into a 6x6. On a new cell, we'll print numpy.resize. We'll resize the y array and it will have 6 rows and 6 columns. So specify a tuple of 6 rows and 6 columns. This outputs a 6 by 6 array, and notice how the data is repeated in order to fill in the extra 3 by 3 rows and columns that we added to it. Another useful function often used to create arrays is np.zeros. As the name suggests, returns a new array filled with zeros. The first argument is the shape of the array. We'll just have it be a one-dimensional array filled with 6 zeros. So we'll specify a tuple of only one dimension. Outputting this, notice how every 0 has a dot. The default type is a float 64. We can make the array elements into integer types by specifying a second argument, a data type, equal to integer. We will explicitly declare every single one of these elements as an integer type. Forgot the comma. There you go. You can go ahead and print this, and one thing to note is that another way to rewrite this tuple is to just omit the comma, and everything should still work out the same way. We can make this into a two-dimensional array of zeros by specifying a shape of 3 and 2, or 2 and 3, whichever one you want. A similar function to this is np.ones, which is essentially the same thing, except that instead of zeros, you'll get ones. Another useful function that's often used is np.i. We'll go ahead and print it, np.i. This creates a square matrix, meaning an equal amount of rows and columns, where all the diagonal elements are ones and other elements are zeros. This is very often used in linear algebraic operations. This will always return a two-dimensional array such that the argument is a number that specifies the columns and rows. If we specify 3, we'll get an identity matrix with 3 rows and 3 columns. Lastly, there are many ways to generate arrays with random numbers in NumPy. For example, we're able to create arrays of random numbers by calling np.random, and we'll use the rand function. This creates an array that can be one-dimensional or multi-dimensional and populates the array with random samples from a uniform distribution over 0 and 1. The only argument being the shape of the array. I want a 4 by 4 array. This results in 4 rows and 4 columns populated by random samples from a uniform distribution over 0 to 1. That wraps up this lesson. We learned how to further manipulate the shapes of an array with the resize method, as well as transpose, flatten, and the ravel functions. We learned about some other useful functions such as zeros, ones, I, and a random number generator.